Okay, let's do this. All right, so yesterday we did some stuff. Now, before we move on, I want to make sure everyone knows. So can anyone remind me what were the formulas for omega, angular velocity? Come on, what was the formula for omega? Omega is equal to, guys, yeah, angle divided by time. What if I have one circle? What is my formula then? Yeah, for a single revolution. Yeah, 2 pi by t. Now, there's one thing I have to clarify, even though the formula is, angle divided by time, but usually in a lot of questions, this formula or this formula is used because they usually give you the time period and they give you the frequency. So in a lot of questions, you literally just use this. Okay, so can anyone please remind me? Yesterday, we derived one of the most trickiest things, centripetal acceleration. Centripetal acceleration. So what is the formula for centripetal acceleration? Can anyone please remind me?
Centripetal acceleration.
Yes, exactly. So AC is V squared divided by R. Now, there's one amazing thing that we can do with this formula. So all of us know that velocity is r omega, right? We know that velocity is r omega. So yeah, so if I take this and substitute into this, I'm gonna get r squared omega squared divided by r. Now you can see that there's an r here and there's an r here. So I can simplify this and I'm gonna get this. And what we've just done, we have derived the second formula for centripetal acceleration. So now you guys know that if you ever have a question on centripetal acceleration, you have two ways to find it. So we can write it down here. All right, now let's make it smaller. Okay, so now there's one thing that I did not tell you yesterday. So if this is my circle, right? This is my circular motion. Where is my acceleration pointing? Come on, guys. If this is a circle, let's say I have a yo-yo, just like we did yesterday, and I'm making a circle. Where is my acceleration pointing? Exactly. It's pointing towards the center. So this is my centripetal acceleration. But there's one thing that I haven't told you, which I'm going to tell you now. In reality, there's two types of acceleration. So we yesterday studied that our velocity was tangential. So this was our velocity. But there's a little plot twist, a little something that's new here. We have another type of acceleration. And this acceleration is called the tangential acceleration. But it's not really, you're just supposed to know what it is. You're not supposed to know a lot about it because this is a concept of not of A levels, basically. So we have tangential acceleration. So yeah, it's going to be a small t. So it's going to be A and a t. So we have AT, and this is our tangential acceleration. Now, the thing with tangential acceleration is, let's say I am at point A. So I'm at point A, now I'm at point B. What I'm gonna do is I'm gonna make this arrow smaller. Now pay attention, I'm gonna tell you why. So this is my arrow, right? This is my tangential acceleration. Now this is my arrow at point B. This is my point B. And this is also my tangential acceleration. Now you're probably wondering, why is my first arrow smaller than the second arrow? Well, this is because tangential acceleration, it increases. So it's not constant. So if you start from point A, you move on to point B, and now you're at point C, you're going to realize that your acceleration is increasing. So as I am spinning my yo-yo, your acceleration is increasing. And there's a real life example. Can anyone, if anyone knows, does any kind of example come to your mind when I say tangential acceleration? Oh, Varun, it's actually, I'm showing you I'm showing you the instantaneous acceleration, but in reality, it is at all points. So if I'm moving from point A and I'm slowly moving here, as I'm moving, my tangential acceleration is actually increasing. So it's everywhere, but it's not constant. It's increasing. So my question for you guys is, what do you think? What is a real life example of tangential acceleration? Just imagine any type of circular motion where your motion, the speed of your motion is increasing. Does anything come to your mind? Okay, fair enough. But the car is supposed to be increasing a lot in its speed. Okay, I'm gonna give you an actual example. So, you know, I don't know if it's done in other countries, but okay, so roller coaster might be, but I'm gonna give you an exact example. So I don't know if other countries have fans, but in Pakistan and India, a lot of houses, they have fans on the, the ceiling. So this is my fan, and the fan looks something like this. There's three thingies, and they spin. So imagine yourself turning on the fan. So when you turn on the fan, you're gonna notice that, allow me to show this process. So let's say this arrow, this is the speed of my fan. So when you start the fan kind of spins slowly, and as it spins, okay, just a second. Okay, so as my fan is spinning, the speed is increasing, and then it starts to spin fast, and then finally, it is doing uniform circular motion. So in the beginning, at the start, the fan is slow. So when you turn on the fan, it kind of speeds up. So a bit slow, and then fast. And then finally, it reaches constant acceleration. So this is the tangential acceleration. So that's why we have two accelerations. So imagine this, when you're turning on the fan, just the first part, when you're turning on the fan and the fan kind of speeds up and finally it reaches that constant motion. Now the constant motion is your centripetal acceleration, but the beginning part, the part at the beginning when your fan is speeding up, that's tangential acceleration. So in real life, tangential acceleration is something that's more practical. But in reality, both of these are applied. Now, if someone is an FSC student, obviously all of us are A-level students. Now, the thing is that in FSC, now you're not supposed to remember this. It's up to you. You cannot even, note it down. So in FSC, what they do is they have the centripetal acceleration over here and the tangential acceleration over here. So when I say that there's an acceleration in circular motion, what I'm actually doing is I'm adding up the squares of centripetal acceleration and the tangential acceleration. Okay, so Varun, so Abdullah answered you. Basically, you're just supposed to know this, just a hint of it. There's not going to be any questions on tangential acceleration and the mixture of these. So my point was just to tell you, no problem. Okay, so now you know that there's two types of acceleration. There's centripetal acceleration, and this acceleration, it's constant in magnitude only. It is constant in magnitude, but AT, it's not constant. Okay, now let's move on. Okay, so yesterday I kind of gave you an idea that we have a force. Can anyone remind me, what is the direction of force in a circular motion? Is it towards the left? Is it tangential? What is the direction of force? Exactly, the center. Now, my force is acting towards the center, and there's a name for this force. This is not just any force. We call it Fc, or in other words, we call it the centripetal force. So this is my centripetal force. Okay, so you guys know that the formula for force, you know the formula for force, right? So can anyone please tell me what is going to be the formula for centripetal force? Yeah, it's F is equal to ma. But what is going to be the formula for centripetal force? You can give me the answer in terms of centripetal acceleration. It's completely fine. Yeah, that's true. Okay, so let's make a heading. Good job, guys. So centripetal force. Now, the first thing we're going to write here is simply MAC. So F is equal to MA. Now, we know that AC has two formulas. So if we substitute the first one, it's going to be mv squared over r. And if we substitute this one, so let's say this is 1, and let's say this is 2. So I substituted the first one into this, and I got this. Now I'm going to substitute the second one into this, and I'm going to get the second formula for my centripetal force. Are you guys clear about this? Does anyone have a confusion on how I derived these two formulas? Okay. Okay, that's great. Now I want you guys to understand something. When we think of force, we think, you know, it's a force. Oh, yeah, lol. So we think it's a force, right? We think it's an actual force. Now, let me give you an actual example. So let's say, I guess I'm just going to go with the yo-yo again. In fact, let's go with a bucket. So let's say I have a rope and I have an empty bucket. This is an empty bucket. There's nothing inside it. So let's say this is my hand and I want to spin it. So I am spinning it and I'm making a circle. So I am spinning the bucket. Spinning the bucket, and I am forming a circle, and we get circular motion. But there's one thing over here that we don't know yet, but now we'll know. Okay, so the force, the centripetal force, is obviously acting from the bucket, you know, from the bucket, from this point where the bucket is spinning to the center of the circle, which is my hand. But exactly, that's what I was about to say. Now, we know that when we spin something, this is a wire, and I'm spinning the bucket with this rope or wire, whatever. And I know that whenever I do this, the rope kind of, you know, there's some kind of tension inside it. And the tension is going to act towards the center. Now you're probably wondering, okay, so this is tension and this is centripetal force. So what is centripetal force? Then you're going to realize that this tension, you know, this tension itself, this is the centripetal force. So the conclusion from this is that centripetal force, it doesn't exist. This is a resultant force. It's a resultant force. It's not an actual force. So if I'm going to give you an example of O-levels, look at this corner right here. So imagine that you have a force acting towards here. Let's say this is some kind of force, right? This is some kind of force of 10 newtons, right? And I have a force in this direction, right? And this is my force, which is acting towards the left, and this is 2 newtons. Now, we know that there's a concept of resultant force. So this is going to be my resultant force. Now, all of you know that resultant force, it's not an actual force, right? This force is just a resultant of these two forces, right? Meaning, in reality, it's nothing by itself. It's just a resultant. But in circular motion, it's a bit different. Now, I'm going to tell you, there's some things that you're supposed to know about this kind of motion. there's we basically subtract tension and weight. But for now, what I want you guys to know is that centripetal force is nothing by itself. It's a resultant force. So in this case, the tension in the rope is providing the centripetal force. So tension in the rope is providing FC. Okay, so Abdullah has a question. Hey, I didn't quite get the question. What do you mean by the equilibrium? Hey, Abdullah, can you please elaborate your question? Okay, no problem. You can just ask me after the class. Okay, so is everyone clear about this? Are you guys clear about the fact that FC is not anything by itself? It's just a resultant force. So in this case, the tension is providing FC. Are you guys clear on that? Come on, guys. Is everyone clear about this? Okay, that's amazing. Now, don't worry, I even made a video on this. It's gonna be a very fun video, and we're gonna watch it a bit later. But for now, we're gonna do a question, a little question. Okay, so does everyone know what's a turntable? Let me write it down. Does everyone know what's a turntable? Is there anyone who doesn't know what's a turntable? Okay, no problem. So, you know, once upon a time, we didn't have phones to listen to music. So we had a disc like this, and there was a needle or something like this, and it kind of used to spin, and you could hear music. So I don't know how you make the music thingy. So a turntable is that, you know, black disky thingy, and when it spins, you can hear music. So that's the turntable. So yeah, exactly. Tom and Jerry, LOL. Okay, so this is our turntable. But in physics, in the world of physics, this turntable is used in a lot of experiments. And I'm gonna show you what experiment we're gonna do. So especially in circular motion, turntables are used a lot. Now, let's imagine that this is my turntable and this is the center of my, you know, the turntable, right? Now, I'm gonna use different colored circles to show you different points. So let's say I have this turntable and I have placed 4 different objects. So point A is my object A, and this is the circle in which it moves. So let's say this is the motion. Okay, now let me make another circle. We're gonna use the yellow for that. Okay, so this is point B. This is object B, and this is the circle it makes when it's spinning on the turntable. Now let's make, let's use a different color. Okay, let's kind of fix it up a bit. All right, so this is point C, and this is the circle it makes. Now we're gonna do one final one, and we can get started. Okay, let's use a reddish color. All right, this is our final circle. And this is D. Okay, so imagine, I know it's it looks kind of like an illusion, some kind of like a hypnosis, but don't worry. So basically, what I made over here is basically, yeah, I guess it's satisfying. So imagine that I have this turntable. So this is my turntable, and I have placed 4 different objects on it. So this is my object A, this is my object B, this is my object C, and this is my object D. And you know, when a turntable spins, the objects on them are also going to spin with the turntable. Now, you can conclude one thing from here. So let's say this is A. So this would be the radius of my circular motion in terms of, you know, the circle. So this would be the radius of the smaller circle. Now, if I use a reddish color, and I'm going to show you the bigger circle. So let's say this is going to be the radius of the bigger circle. So we're going to be comparing the red circle and this reddish circle, right? Now, my question for you is, you know the formulas, right? We have two formulas. This is formula 1 and this is formula 2. My question for you is, you can take your time. Which one of these, A or D? So which one of these, A, or in fact, I'm going to give you an open option. So which one of these is gonna have the greatest centripetal force? Come on, guys. This is a question for you. Let's see who can answer the question. Okay, so everyone has the same answer. Okay, come on, everyone. There's like, how many people do we have here? Okay, so we literally have 11 participants. If we kind of don't count me, it's 10. Okay, so the students are even giving out their versions of why this is the case. Come on, has everyone answered? We have a lot of students here. Okay, so I guess I assume. Okay, so Abdullah, you're a genius, LOL. This seems like a nice point. Now, let's observe the situation, right? We have two formulas. So let's say, formula 1. So according to this formula, you're going to be like, all right, so I have mass. Mass is obviously constant, right? And we have velocity. So you're like, okay, so I think that, in fact, let's leave velocity for a second. You're like, okay, so FC and R, they seem to be inversely proportional. So this is your first thought. This is not the right answer. So you're going to be like, okay, so FC and R, they seem to be inversely proportional because I have this equation, right? So FC, you're going to be like, okay, so I think that the one with the smallest radius has the greatest centripetal force. And you're going to be like, okay, so my answer is A. Now, that's if you follow this equation. Now, if we follow the second equation tells us that FC and R are directly proportional, right? So according to equation number 2, you're going to think that, okay, so the greater my FC, the greater my radius. So the larger my radius of the circle, the larger my FC. So according to this, the answer is D, but according to this, the answer is A. So can anyone tell me which one of these equations is the right one and why is the one that's wrong? Okay, so Sabina says radius is inversely proportional to force. Okay, so Varun, that's the point that I've been looking for. That's kind of right, but that's still not it. That's still not it. Okay, let me explain you. Okay. Oh, by the way, guys, if our meeting suddenly ends, if our class suddenly ends, know that the time, the Zoom time limit is up. So I'm just going to send you the link again and you can join the class again. So don't go anywhere if the class suddenly ends. All right. So according to Varun, he said that, okay, so I'm looking at equation number 1 and I think, yeah, I'm going to explain that. So Varun's thought was that I think that if, I know that velocity is, I know that V is R omega. So what I'm going to do is I'm just going to substitute this into this and I'm going to get this equation. So if you put R omega into this, you are going to get equation number 2. But that's still not a valid argument. I can also say that omega is V by R and I can literally just substitute this into that. So this reasoning is just, I believe this is not the accurate reasoning. I think this is the right way of saying, but it's not the right answer. So because if you substitute this thing, omega is equal to V over R into this, you are gonna get this equation. Now, I'm gonna tell you the actual reason. So whenever you say that something, exactly, right answer by Alian. Okay, so in this equation, are you guys sure that both mass and velocity are constant? Yes, I know that omega, wait, but is omega constant? Okay, let's observe the situation. I haven't, what is omega? Let's look at omega. What is omega? Omega is 2 pi over t, right? So according to this, if my time period is constant, and obviously it's going to be constant, has it ever happened that if I have object A and object D, and when I start spinning, it turns out that object D is behind object A. So when I'm spinning the turntable, when the turntable is turning, all 4 of these are going to be in the same spot. Has it ever happened that it's literally one disk? It's one disk, and I have, let's say, A and B, and now it's spinning, and at the end of the the turn, it turned out that point B is over here and point A is over there. That never happened. All of these objects, they always remain where they are. So I can easily say that according to this, the time period for all of these is constant. So we're going to say one thing over here. So time is, the time period is constant. And because my time period is constant, I know that omega is constant, right? Now, we're going to get to the most important point. Is velocity constant? What do you guys think? Is velocity for these 4 objects on the turntable, is the velocity constant? Because if it is not constant, you can never say that Fc and R are inversely proportional. Unless your velocity is constant, this relation can never be true. Exactly. Now, let me explain my point. What is the formula for velocity? V is equal to R omega, right? And I just proved that omega is constant, right? So I know that velocity is directly proportional to the radius. Isn't that true? So that by this logic, I can say that A has lesser velocity as compared to D. Isn't that true? Now, for a second, let me erase C and B just so I can compare them. Now, let me explain this point. So the answer is D, all right? So the answer is D. Okay, so the answer is D. Now, let me explain one thing. Let me prove this fact. So I know that the time period is the same. So let's say I have an arrow. I'm going to use this arrow. Now pay attention, please. Okay, so I have this arrow over here. Now, let's say that, okay, the yellow color doesn't seem too cool. Let me change it to blue. Okay, let's use blue. Okay, now, let's say that this is my point A, and it is moving, with the turntable, and it is completing the circle. So it has lesser. Now tell me one thing. Which one of these, A or D, which one of these has to travel more distance to complete one circle? Just look at the sizes of the circles. Exactly. So if you actually use your brains for a second, you're going to realize that, okay, so point D has to travel way more. It has to travel way more than A to complete the circle. And we know that time is constant. So I know that the time period is constant. So if the time is the same, can I say that A can travel the same distance as D with smaller speed? So A is going to have lesser speed and D is going to have more speed. Why? Because it has to travel so much more distance in the same time as A. And if their speeds were the same, then the time wouldn't ever be the same. Does everyone understand this point? Why the speed at V is lesser and why the speed at D is more? Okay, that's amazing. Now, we know that the speed is not the same. So this relation is not true. So Fc is not inversely proportional to R. So I can just cross it out. Now, I know that omega is constant, and I know this as well. So I know that Fc is directly proportional to r. So that's my actual reasoning for this question. So now you know that if I compare point A and point B and point D, the point D, the object at point D is going to have greater centripetal force. So it's going to have greater FC. Does everyone understand this? So never forget it. But keep in mind one thing. The turntable is one disk, right? This is one system. So this is one system. Let me tell you why I said this. Okay, so take the screenshot, and when you guys are done, tell me, because I want to tell you something mind-blowing. I mean, it's not mind-blowing. It's just something cool. Okay, are you guys done with the screenshot and notes? Okay, so I'm going to erase this. All right, amazing. Now let's clear this up. Now, exactly what. Now let me explain you what I mean by that. So, you know, all of us know what our solar system looks like. Okay, so Legina, you have a question. You just raised your hand. So Legina, do you have a question? Okay, no problem. Okay, so this is my sun. You know, this is the sun. Now, obviously, I cannot show you the ratio of the planets, but let's say this is my Earth, right? This is Earth. And I mean, I don't know all the planets, LOL, but let's just say that we are comparing this to the Jupiter. Let's say this is Jupiter. Okay, right? Now, you guys know that obviously, if the time period was constant, right? Okay, so let's say after today's class, if I didn't tell you this, you would be like, okay, so today I was taught that the time period is always constant when, you know, in a system that turns. But all of us know that for Earth, 1 year is 365 days. But is it the same for Jupiter? Obviously, no. I mean, to be very honest, I don't know what's 1 year for Jupiter, but it's obviously not 365 days, right? So I don't know. Yeah, the math is different. That's a different concept. So this is not one system because the planets, they're not even touching each other. Okay, so that's not a good explanation. So a turntable, this is one disk, right? This is literally one disk. So a turntable is one system. This is one system, but these are two systems. These are, you know, these are two systems. So the time is not constant. So you're not supposed to note it down because we're going to do it in gravitation, but I just wanted to clear this up. Okay, so now you know that to have omega as a constant, it has to be the same system. All right, now we're going to study a very interesting concept. I'm going to write one statement, and then I'm going to explain what does it mean. So the statement is that gravity always, okay, where's my pen, LOL? Okay, just a second. Okay, so gravity always opposes a push or a pull. A gravity always opposes a push or a pull. Now, let me explain what this means. So we have a situation here. Okay, so let's just hope I make it nice. Okay, so let's say this is a person, right? Now, let's make a little neck here. Let's make the body. Let's make the arms. Okay, I don't have time for fingers and all. Okay, so let's say he has clothes on, so don't get misconceptions. Okay, so this is the center, and I have two arrows. Okay, so I have two arrows. Okay, first let's make the ground because he's obviously standing on a ground, right? So this is the ground. So this is our ground. Now, we know that gravity is acting downwards, but we also know that the normal reaction force, the normal reaction force is acting upwards. And we know that gravity is acting downwards. Okay, let me erase this. All right, so the gravity is acting downwards. Okay. Okay, so gravity is acting downwards. So, oh, okay, I made it a bit not right. Okay, it's supposed to be straight. All right, I think it's fair enough. Okay, so this is my gravity, and this is my normal reaction. Oh, this is my normal reaction force. Now, this normal reaction force is more of a push, right? Because I know you might get a bit confused. So when I'm standing on the ground, let's say this is my foot. Now, it's for those who might not get this point. So you're obviously pushing on the ground, right? Your foot is pushing on the ground, and as a result of that, you are getting, okay, where's my drawing, LOL? Okay, so you are applying force on the ground, right? And as a result of that, there is a normal reaction force, and that is upwards. So that's why I am saying that normal reaction force is a push. So don't get confused. You're obviously pushing on the ground, and the reaction of that push is upwards. Okay, so do you guys understand this? Exactly, bro. Because when you punch a wall, you feel pain. Exactly. That's kind of true. Okay, so do you guys understand this? That's amazing. Now, let's make another situation. So, let's say somehow I have a ceiling or something. LOL. Okay, so I have a ceiling, and one day I'm like, okay, so I wanna hold a rope, and I wanna, okay, let me make this. I don't know how to say this. Okay, so this is a wire or something, and one day, let's say your day wasn't going so well, and you decided to hang yourself. I mean, not in that sense. I mean, just for fun, you decided to hang on the ceiling, and like this. Okay, so these are your feet, and this is you. LOL. Okay, so now we know that there's obviously, we've been doing this since O level, so there's obviously a tension in this rope, and tension is acting upwards. Now this tension is more of a pull. So we're gonna write it pull, right? This is a pull. The tension happens as a result of a pull. So this is a pull, and the result of that pull is, it's actually the gravity. Okay, so now the gravity is opposing this pull. So this is my gravity. So the gravity is opposing this pull. Now, let's upgrade the situation into something else. Let me make it for 1 second. LOL, how do I make it smaller? Okay, it's smaller now. Okay, I don't know what I just did. Okay, let's move it. All right, so now, let's say I have the same wall, and I got bored. I wanted to, okay, this is flipped. Okay, so I wasn't having so much fun just by hanging. Hey, it says my internet connection is unstable. Is my voice lagging? Because I just got a notification that my internet connection is unstable. Okay, okay, that's great. Now let's move. All right, so now I wasn't having so much fun just by hanging on this rope. I decided to swing myself. So let's say you kind of wanted to have some fun, and you decided to swing in your room like Tarzan or something. Okay, so you wanted to impersonate Tarzan. So let's say you're a, okay, it's lagging. Oh, I see. Is it good now? Is my voice not lagging now? Because, okay, it's great. You guys can hear me, right? Everything is fine now, right? Okay, that's amazing. Now, so you wanted to be, the Tarzan. and you're swinging in your room. So let's say you're making this, you're doing this motion, right? Now, the pull is in this direction, but the gravity, the gravity is downwards, right? So let me make the arrow for the gravitational force. So this is the gravity, right? The gravity is acting downwards. But why is your body like this? Doesn't it look like as if there's gravity over there, right? So if you would ask someone and your body was like this, you would logically think that there's a force that's, that's pulling you from here. That's why your body's like this in the first place. But in reality, the gravity is downwards. Now, this is where this term comes in. Gravity always opposes a push or a pull. So if my pull is here, the gravity is opposing this. Yes, don't forget that the gravity is actually downwards, but this is our perceived gravity. This is the perceived gravity. And this is what I wanted you to understand. Do you guys understand it? So the gravity, LOL bros. Okay, so the gravity is acting downwards, but because gravity opposes a push or a pull, we make an arrow over there. And this is the perceived gravity. So let's call it, this is the perceived gravity. Okay, now there's another situation that I want you guys to understand. Okay, now everyone pay attention. I'm gonna teach you this concept, and once it's uploaded, I'm just gonna share the video. Okay, now, imagine I have a car. Imagine this is a roundabout, and this is my car. So, this is our little Ferrari or something like that, and it's moving in a circle, and this is my circle. Now, you guys know that centripetal force is a resultant force. What is providing centripetal force in this scenario? What do you guys think? Okay, so that's a close answer, but that's still not it. What do you guys think is providing the centripetal force? Okay, Varun. Okay, I'll repeat the question. My question is that I have a car, a really cool car, and it's moving in a circular motion. What is providing the centripetal force in this scenario? That's my question. And Varun has the right answer. Okay, so for those who didn't get it right, no problem. We know that, in this motion, our car, let's say these are, these are our tires. So we know that the tires have a frictional force with the ground. And this frictional force is the one that provides us the centripetal force. Do you guys understand it? Does anyone have a confusion? Friction provides FC. Okay, does anyone have a confusion about this? Come on, guys. I just have one answer so far. Okay, that's great. That's amazing. Now, let me contrast this into a situation. So you know that when we travel in the city, we don't always have straight roads. We have sometimes curved tracks, right? This is the road, and my car is traveling over here. Now, we know that the car will have to turn. Now, the amazing thing is when it's turning to the left, that is circular motion as well. And we know that since this is circular motion, there's going to be a centripetal force acting towards the middle. And all of us know that if our car, if it's traveling at a very high speed, a very high speed, there are chances that our car is gonna skid. The car is gonna move to that direction. Why do you think that happens? Our car is making a left turn, and if it's traveling at a high speed, the car skids. The car skids. It moves to the right. Why do you think that happens? But that's still not the answer. Okay, Abdullah, that's the right answer. So we know that to stay in circular motion, right? If you wanna maintain your circular motion, if you wanna move in circular motion, your centripetal force has to be, fulfilled. So when your car is traveling at a high speed and it's over here, and the fact that it skids towards the right, that means that the car does not have enough centripetal force. Oh, it does not have enough friction. And you know that friction provides the centripetal force. So let me first write over here. So friction with the road provides the centripetal force. So we know that friction provides